welcome back. Today we're gonna continue about the math and molar fluxes. In previous video, we have talked about Fick's law of binary diffusion or molecular transport. So we would rewrite the equations look like this. So J small j a y equal to minus rho dAb, which is the diffusivity of AB, d of the mass fraction of A divided by dy, which is the distance. So this is the gradients or the driving force, and also this is the gradient for the distance. Okay, so this Fick's law is only used for molecular mass flux. Yeah, so J AY is the molecular mass flux of helium in the positive of Y direction. Note the first index A designates the chemical species, in this case helium, and the second index indicates the direction. So the Y is the direction. Alright, now let's just jump up to page, this is the chapter 17.8 about summary and the mass molar flux. Okay, so in previous one here. Okay, so first we're gonna talk about the definition first. The first one is mass and molar concentration. A mass concentration, or rho alpha, is the mass species of alpha per unit volume of solution. For molar, if you know, you always say concentration, or C. Concentration is actually the number of moles of alpha per unit of volume evolution, or we can call it rho A divided by the molecular mass of alpha. And we also can introduce a term of mass fraction, or omega alpha. For this case, omega alpha is actually equal to rho alpha divided by rho, or X alpha. Yeah, the mole fraction. Mole fraction is actually concentration of A divided by the concentration of mixture. So this is the definition of mass and molar concentration that we will use in the next equations. Okay, in diffusing mixture, there are various chemical species are moving at different velocities, one to this side, one to that side. So rather than by writing V A in vector, because it's in bold, or velocity of species A, we do not mean that the velocity of individual molecule of species of A, rather than we mean the average of the velocity of molecule in vector of species A within small volume. So for let's say a mixture of n species, the total mass average velocity we can call it V equal to summation from alpha equal to 1 to n species rho alpha V alpha divided by the summation of the rho alpha. Yeah, so it's actually the summation of from alpha equal to 1 to n from the each mass fraction of alpha multiplied by the velocity of alpha in vector. And so we can see in table 7.71 the notation. Yeah, here there is in basic definition in term of mass. You can see the mass concentration, the mass density of the mixture, or the mass fraction of species, or in the term of molar, there is a molar concentration, there is a molar density, and also the mole fraction. And you know the molar mean molecular weight we define as capital M equal to rho divided by C. So you can by that you can build an algebraic relation. What is the relationship between concentration and mass density? The summation of for example mole fraction is 1, the summation of mass fraction is 1, and how to calculate mass fraction if how to calculate mole fraction if compared with mass fraction and its molecular weight. And also if you want to see, this is the divergence, the differential relation for fraction A, and also the divergence of mass fraction A. Okay, so um, using this equation, we can define, we called it V star, or molar average velocity is actually a summation from alpha equal to 1 into n between the concentration, or the molar concentration of alpha multiplied with its velocity divided by the summation of concentration, or we can call it equal to summation from alpha to 1 to n is molar fraction multiplied with its average velocity of A. So if V star we multiply it with concentration, okay, so C is concentration. If we multiply it with velocity, that's gonna be the flux, yeah, it's gonna be the molar flux, or the log rate which mole pass through a unit cross section placed perpendicular to the molar velocity V star. Okay, so mass flux is actually C multiplied with V. Yeah, mass flux or molar flux is actually equal to molar concentration multiplied with the velocity. Both mass average velocity and the molar velocity average will be used extensively through the remainder of the book. Yeah, so for velocity in multi-component system, we gonna define it with some basic definition. V alpha is the velocity of spaces A with respect to a fixed coordinate. V actually is the mass average velocity. V star, yeah, the term star is the molar velocity. The difference, or V alpha minus V, is actually the diffusion velocity of spaces A with respect to the mass transfer of the average velocity V, while V alpha minus V star actually the diffusion velocity of spaces A with respect to the molar average velocity. Okay, now by that we can see go back to the chapter 7.17.1 in fixed first law diffusion to describe how the mass of spaces A in binary mixture is transported by means of molecular motion. Okay, so if you remember in the beginning, there is a small ja is actually equal to rho, yeah, a concentration multiplied with the velocity. Okay, remember, flux equal to concentration multiplied with velocity. So for this case, Ja, which is this is concentration, mass concentration multiplied with its velocity, yeah, or equal to rho multiplied with dAb multiplied with the divergence of its mass fraction. In the term of molar unit, we can call it capital Ja in a star equal to concentration of A multiplied with its velocity. If you say diffusion velocity, which is the difference, with equal to the minus concentration of the mixture multiplied with dAb multiplied with divergence of the mole fraction. So the term of difference is Va minus V, and Va minus V star is sometimes reversed as diffusion velocity. Okay, now let's consider the first part is the molecular mass and or molecular flux. Now consider the convective mass, or the convective mass, or convective mass fluxes, or convective molar fluxes. So in addition to transport by molecular motion, mass can also be transported by the bulk motion, which is there is a velocity in it. So the mass just transfer because of there is a bulk motion of the fluid, because of the medium is flowing. Yeah, so Okay, so we can call that the velocity is called the mass average velocity. Yeah. So if we check it here, if we try to multiply it, it's actually equal. So the convective mass or molar fluxes for mass fluxes is equal to rho of alpha multiplied with its velocity. And this is called the convective mass flux tensor, the convective mass flux vector, which has unit of kilogram over meter square multiplied with second. If we change it into the molar, it would be equal to the molar concentration of alpha multiplied with the V star. Yeah, unit of kilogram mole divided by square meters multiplied with second. So, to get convective mass and molar fluxes from a unit surface, whose normal unit vector is n, we form dot product, and so this dot product. This is n multiplied with rho v or n multiplied with concentration of alpha multiplied with v star. Okay, so so we have learned there is a JA, which is the molecular flux, molecular mass flux, and also there is a convective mass flux, rho alpha multiplied with V. So the combined mass flux, we would call it a small n alpha. For molar flux, we put a capital, so a capital N alpha, equal to J alpha star, which is this is because of the molecular, and this is the convective. Remember in momentum, you also learn there is a momentum, there is a molecular part, there's also convective part. In heat transfer, you learn there is a molecular part, which is the conduction, and also there's a convective part. In this case as well, the combined molar flux or combined mass flux is denoted by N. So if we write it up, if we write it up, we can write JA equal to N minus rho V, where rho V is actually the mass fraction of alpha multiply with the sigma and beta. If we simplify all this relation, we can go back to this equivalent form of Fick's law in table 17.8 strip 2. This is NA, and this is small a. So for example, for mass, NA, which is the combined mass flux, which the gradient is the divergence of mass fraction or omega A, NA would be equal to omega A multiply with NA plus NB minus rho dou DAB, we multiply with its divergence. Okay, or if it is in molar, we can call it NA would be equal to XA NA plus NB minus CDAB divergence of XA, or where CDAB minus XA is the first law of Fick's law, which is this one, the JA star. Okay, so that's all. So the equivalent form of Fick's law binary diffusion, now we can write we have to know the relationship between the Na, which is the combined mass flux, with what is relationship with Ja, which is the molecular mass flux.